I think I figured out that I just need to stop complaining. I went to SI and I also went to office hours, and it turns out that electric potential really isn't that hard. We know that the work required to get something from point A to point B is going to be the integral from A to B of f dot ds. We know that from last semester in Physics 151, or Physics 1. And the work is going to be the same no matter which path you travel along from A to B. The work is path independent. We can also write work as delta U, the potential energy from the final position minus the potential energy from the initial position. So let's try and put this in terms of electricity. We recall that the force acting upon a charged particle in an electric field is equal to the product of the particle's charge and the electric field. So we can substitute that back in for F. And because Q is constant, and this is an integral, we can pull it out of the integral. And we can divide both sides by the charge Q. And so it's going to turn out that this is going to be equal to VA minus VB, or delta V, which is our voltage drop across the 2 points. By the way, voltage is in terms of joules per coulomb. So let's try and use this golden little relationship to solve a sample problem, shall we? For my sake, just please imagine that these are circular. So we have a conducting spherical shell surrounding a point charge. The point charge has charge negative Q, and the shell has charge plus 2Q. The shell has an inner radius of A and an outer radius of B. We are going to need to find the electric potential, the voltage, at 3 regions: inside the cavity, inside the shell, and outside the shell. First, let's find potential for R being greater than B. Let's choose an arbitrary point outside the shell that is a distance r away from the point charge in the middle of the shell. In order to find the potential, we need 2 points. But we need a point that is further away from the shell than this one. And that's where things get a little tricky, because there aren't any points inside the shell that are greater than this one. But we know something that can actually make it a little bit easy. Because somewhere out in the ether, r is going to equal infinity. And that is actually going to make our integral pretty easy to solve. We know that the electric field is going to be equal to Q inside of the Gaussian over A times epsilon naught. For a Gaussian with a radius larger than the shell, the charge inside of the Gaussian is going to just be equal to the sum of all the charges, which in this case is positive 2Q minus Q, or just Q. Area is going to be the surface area of a sphere. So let's recall our integral for electric potential, but this time we are going to be plugging in E of R times dr. E of R is just the electric field equation that we found up here, and dr is the displacement. Because if you are going to travel from this to this, you're going to have to travel along R. So we integrate along R. So this is what we have, and our bounds are going to be from r to infinity, because that's where we're integrating along. All of this is constant, so we can pull it out of the integral. We integrate, and we get that the answer to this is going to be Q over 4 pi epsilon naught times negative 1 over infinity plus 1 over r. And as we know, any constant divided by infinity goes to 0. So finally, we get that the voltage anywhere where R is greater than B is going to be equal to the charge Q divided by 4 pi epsilon naught R. Now we want to find the electric potential for some R inside the shell. It's going to be between the inner radius A and the outer radius B. Let's remember that this shell is a conductor, so it has several special properties. In order for the electric field inside the conductor to be 0, the charge of the conductor is going to need to migrate to the inner surface of the shell and the outer surface of the shell. We are going to have a positive Q to balance out the point charge of negative Q inside the inner surface, and the other positive Q that we're left with is going to try and get as far away from that positive Q as possible, and it's going to migrate to the outer surface. This makes it so that if we take any sort of Gaussian inside this shell, the electric field is going to be 0. So in order to find the electric potential inside this thing, we are going to need to be a little bit unorthodox. Because the voltage is equal to the integral of the electric field dotted with the displacement vector, and since the electric field inside this area is going to be 0, we know that the change in R is also going to be 0. So there is going to be no change in voltage inside this conductor. And that's true for all conductors. In a conductor, there is no change in voltage, which means that the voltage at our point R and the voltage at B are going to be 0. So that means that these two values are the same. And that's another property of conductors. The voltage inside the entire conductor is going to be just equal to the voltage at the outer surface of the conductor. We already found the voltage equation in the last part, so now we just need to plug B in for R. So that is going to be our voltage inside any point in the shell. This is the electric potential for any R that is less than A, but I'm going to be completely honest, I don't really get it. It has something to do with the properties of conductors, but what, I'm not quite sure. I'll probably ask my professor tomorrow. Lastly, for physics tonight, let's quickly touch on partial derivatives. A partial derivative of a certain function with respect to a certain variable means that you are taking the derivative of that function, but imagining that all variables except the one that you're taking the partial derivative with respect to are constants. It's a mouthful. Let me just do an example. Let's imagine that there is an equation v of x comma y comma z that is equal to v naught over 2d times x minus cube root of 3 times y. If we are taking the partial derivative of v with respect to x, we are imagining that all the variables in this equation except for x are constants. We see that the cube root of y is just going to be a constant because a constant times a constant is a constant. You think I can say constant more times tonight? I haven't even gotten started yet. We use the product rule, and we get that the partial derivative of v with respect to x is going to equal v naught over 2d. Now let's take the partial derivative with respect to y. Once again, we use product rule, and we are left with negative root 3 v naught over 2d. The partial derivative of v with respect to z is perhaps the simplest to find. But let's take a look at what this is actually asking us here. The partial derivative of v with respect to z is asking us to imagine that all variables in this equation besides z are constant. But there is no z, so it's just asking us to imagine that all variables are constant. And if all variables are constant, then that means that the entire equation is a constant, and the derivative of a constant is 0. So that's simple enough. These partial derivatives actually allow us to do the reverse of what we've been practicing previously. They allow us to find the electric field vector if we are given the equation for electric potential in terms of x, y, and z. Let's imagine that this is an equation for electric potential at a certain point. I picked up the wrong marker. The electric field in the x direction is going to be equal to the negative partial derivative of v with respect to x. The electric field in the y direction is going to be the negative partial derivative of v with respect to y. And the same pattern applies for z. If we add up all of these vectors, then we are going to get a total electric field vector. We say that the electric field is equal to the negative gradient vector times v. All this is saying is that the electric field is equal to the sum of all of these negative partial derivatives. Okay, I think that sets me up pretty good for lecture tomorrow. Now, on to public policy. There are around 28 practice questions I have tonight and tomorrow night, so I'm going to go rapid fire through around half of them tonight. That should set me up pretty well. Describe the process for U.S. naturalization. If a person is born outside of the United States and their parents are not U.S. citizens, in order to become a U.S. citizen, they need to be naturalized. You need to either be a permanent resident for 5 years, be married to a U.S. citizen for at least 3 years, or you can fulfill some other sort of military service requirement. There are a few different pathways to residency here in the US. You can have family living here in the US already. That makes it easier to get a green card. Your employers could sponsor you. You could come here and live here for work. If you can prove to the US government that your life is in imminent danger and you need to come here in order for your own safety, you can try and get one of the limited refugee spots. Or lastly, you can enter the diversity lottery. You get randomly selected out of a pool of millions. After you've been a resident for 5 years, married to someone for 3 years, or completed military requirements, you need to take a test. The test is on knowledge of US civics and the English language. In the English portion, there is a written portion and a spoken portion. If you've completed all the requirements and you pass this test, you get naturalized. What are the main characteristics of democratic citizenship? There are 3 main ones, the first being a sense of belonging. The second being a citizen in a democratic system gets to participate in that system. Lastly, certain rights are guaranteed in a democratic system that are not guaranteed in other types of systems. Describe Marshall's topology of rights. Marshall split up rights into 3 main categories. A right is political if it has to do with a citizen participating in government or lawmaking. Civil rights protect an individual's ability to make their own decisions. Social rights set an individual's basic living standards. Social security and free public education are examples of social rights. Describe recent trends in voter participation. Over the last few decades, voter participation has been steadily decreasing due to a number of factors. Overall, there is less of a trust in the government than there was before, and if you don't trust your government, why do you think you would want to vote? There is an increased apathy and exhaustion these days. People see their government being incompetent and are less likely to participate in the system. There are 5 long-standing principles that govern US citizenship. It is easy to acquire, hard to lose, allows dual citizenship, there are no distinctions between citizens, and there are distinctions between citizens and non-citizens. I wanted to get through 14, and I got through 5. Well, that's all the time that I have in this room. I'm not too worried about this test, but it is going to be important for me to go over the rest of these questions tomorrow. Because if I can get these questions down, I'm pretty sure that I'm going to do well on the test. In the meantime, thank you so much for watching. See y'all tomorrow.